What search algorithm assumes that all actions have uniform cost? Breadth first search. Yeah, sneaky trick question because this one's called uniform cost search. Why is it called uniform cost search? Because everything in the frontier has a uniform cost. Choose the best action. Complete this statement. With A* search, the heuristic must underestimate the largest cost incurred so far. We know the cost incurred so far with precision. Why would we want an estimate of it? Right? Okay. Why would we want to overestimate it? That doesn't make sense either. Does it multiply by the fastest speed that can be traveled over any region of terrain? So that is something we did when using A* search. Is that something you always do in A* search? No. Why did we do that in A* search? Yeah, we wanted to ensure we were underestimating the remaining cost, and the cost depended on the speed. And why did we pick the fastest speed? Because that has the lowest cost. And that is one, I guess you could say, cheap hack way to ensure that we're underestimating the remaining cost, which pretty much I just gave you the answer. This is the answer that is general and always applies to A* search. Just to finish going through the distractors, does A* search use Euclidean distance to estimate the remaining distance to the goal? This is usually what people do with A* search, but that is nothing built into A* search. That's just what people usually do. So I admit that was a sneaky, dastardly distractor, but if you understand A* search, you should understand you only need to underestimate the remaining cost. Euclidean distance is one good way to do that. It is not the way to do that. And there are cases where that is not an underestimated, this does not underestimate the remaining cost. For example, if there's a wormhole, or if there's something that violates the triangle inequality, or something that is, or if you're optimizing something that isn't in spatial domains, actions to wash the dishes, there's no real Euclidean distance there. So there's lots of cases where that's the wrong thing to do. And I'd rather you really understand A* search, so no, that's not right. Does it overestimate the remaining cost to reach the goal? What happens if you do that? Yeah, in fact, you will get a suboptimal goal. Well, not for sure, but usually. Well, the only thing I can tell you this does is it destroys the guarantee of optimality. Very often, it turns it into greedy search. And if you overestimate it by a lot, it definitely turns it into greedy search. And that's not necessarily bad. If you want a really fast path, if you want to find the path to the goal really fast, greedy search is a great way to go. But as soon as it gets stuck, then it finds a really suboptimal solution, and that can end up even taking longer than the original. Does it choose the action that minimizes utility? I don't even know what that means. Does it choose the action that marginalizes probability? That means even less. And kind of technically, A* does minimize utility, but it minimizes it minimizes cost, which is the opposite of utility. It maximizes utility. So it almost makes sense, but it's the opposite of that. And marginalizes probability, that's something totally different. Okay, which one of these algorithms always finds the optimal goal in the least amount of time when implemented properly? Yeah, that's the answer. So these always find the optimal goal. But A* is guaranteed to have a computational cost less than or equal to uniform cost search. Therefore, why would you ever pick uniform cost search as the one that finds it in the least amount of time? Now, admittedly, they could be the same if there is no possible good heuristic. But usually there's something that's a reasonable heuristic. So you can usually beat uniform cost search at least by a little bit. And if you have infinite knowledge, you can beat it perfectly by using a perfect heuristic, which makes this as fast as greedy search. Okay, breadth first search's real problem is that it's not suitable for all problems. Specifically, it's not suitable for problems where the costs are non-uniform. So anyway, A* search clearly beats these. What about genetic algorithm? Isn't the whole point that it's faster than A* search? Yeah, well, that's kind of the case in some cases. So genetic algorithms are neither faster nor optimal in low-dimensional spaces. If you try doing A* search in high-dimensional spaces, you will find that it gets slow really fast. And genetic algorithms don't get any faster, but they start looking a lot more appealing when everything else poops out. In the domain of AI, this is called the curse of dimensionality. As the number of dimensions gets larger, the size of the space grows exponentially with respect to the dimensions, usually. That's not always the case, but it usually is. And so algorithms just grind to a crawl, especially systematic ones. The reason genetic algorithms do so darn well in high-dimensional spaces is they aren't systematic at all. They're very ad hoc. They just kind of try stuff, and if it works, they keep it around for a while. And if it keeps working, they keep it around some more, and if it doesn't work, it kills it off. But you see how they're really the same algorithm? It's just genetics are a lot less systematic, and A-star is a lot more systematic, but they're still doing kind of the same thing-ish. A-star, the top three are the only ones that satisfy optimal goal, and the bottom two are the only ones that satisfy could be the fastest, therefore it's that A-star. Which one of the following refinements would make the biggest difference in reducing the memory footprint of breadth-first search? This question actually came up. The reason this one came up in past years is because on assignment 1, the one where we do solving the puzzle, we use breadth-first search, and I didn't originally tell everybody use an array of 21 bytes, 22 bytes? 22 bytes for the state of the puzzle. And everyone in the class used different ways of encoding their states, and I had so many people doing things that encoded all the shapes of the puzzles and the colors and this big object-oriented hierarchy of state for the puzzle. Because that's kind of the natural thing a programmer does, right? You write a bunch of classes and you build an object-oriented hierarchy, but do you see how that assignment turned out? When you make 100 billion instances of this whole hierarchy, it basically swamps your memory, and everyone learned really well that's not the right thing to do when you're making 100,000 instances of something. Since I just told you what to do, I bet a lot of you didn't catch this to quite the same extent, but what would you do to make breadth-first search more efficient with respect to memory? That's what this one is, and yes, it does actually work. It doesn't reduce the footprint, yeah. So that one's technically not right. This is the right answer. The reason is because if you use a smaller encoding of state, it's that size multiplied by 100 billion, because that's how many states you have to search through, right? Why do you search through 100 billion states? Because breadth-first search is one of those systematic algorithms that searches everywhere. Okay, which is more important, memory or speed? It totally depends, right? It always depends. But if it's too slow, what do? You wait longer. If it runs out of memory, what do? Yeah, see, when you run out of memory, you're kind of hosed with modern computing architectures, whereas if it's too slow, well, you can deal with it. So it's often considered that memory is a bigger deal than runtime when it comes to algorithms that are trying to be systematic or brute force or something like that. Of course, using a genetic algorithm will totally solve all of your memory problems, but it wasn't an option, and it will destroy your optimality. What would happen if you implemented a genetic algorithm with no selection operation, meaning no member of the population is ever killed, on a single computer? As I looked through the answers on this one, it became clear to me that when I taught genetic algorithms, I tried to make it clear that we were just doing one way of doing genetic algorithms. It's more of a theme of algorithms than it is really a specific algorithm. Did that come across? Well, the idea of no member of the population is ever killed, I don't think everybody caught quite what I'm meaning, and I hate to take off points for playing the guess what I'm thinking game. Well, basically what I meant by no one is ever killed, I meant the population will only grow. Now, some of you assume that if no one's ever killed, that means no one's ever born, and that is kind of because you assumed that our implementation was the way to do it. Using a fixed size matrix is not a genetic algorithm thing. So having clarified that, would the computational cost increase as the size of the population increased? It definitely would, because as the population increases, you have to work with more people. It takes longer before they're going to evolve. Now, to be clear, the computational cost of doing a single pass, well, the computational cost of randomly picking a row and mutating it would be the same, right? And the computational cost of randomly picking two individuals and having them fight would be the same, right? But the computational cost of making progress, making some amount of progress. I don't know how you would even quantify that, but if you could, that would definitely be more computationally expensive. So there's a little bit of room for debate on here, and I'm going to admit it wasn't a great question. Well, it wasn't a well-defined question, so to speak, but I do think it made you think about things. But I think that by asking this, by saying as the size of the population increased, certainly made it clear that the population was increasing. Would mutation have no effect? Why would it not? All that would do is change things. It would have a less impactful effect because you're impacting a smaller portion of the population per mutation, I suppose, unless you increased your mutation rate, or if your implementation was every member of the population has X% chance of being mutated, then it would have the same effect. So either way, it has some effect. Would randomly chosen parents would be more likely to produce good children? I'm going to claim it's exactly the opposite, because if nothing ever dies, you've got all the bad regions of the space still hanging around. And what's actually going to happen is those bad regions of the space are going to keep breeding with the good ones, making bad children, and you'll never really make any progress. So this is going to totally destroy your progress. So that one's a definite no. Would the diversity in the population converge to 0? Also the opposite. Yeah, I mean, we're going to have creatures all over the place because everything's still alive. Would it be more biologically plausible? In other words, does death exist? Okay. Would bacteria overrun the population? Some people put some assumptions translating bacteria into something that made sense in genetic algorithms, and so I had to consider those ones separately. But in general, if there were no assumptions stated, there should be no bacteria in your genetic algorithm because we're not doing it in biology, we're doing it in a computer. I hope that was clear. Okay. That was the only answer that I wanted. And that one's slightly debatable. Anyway, there we go. Can A-star search offer computational improvements over breadth-first search if all actions have uniform cost? So this thing right here was pretty much a distractor. Does that change anything at all? It doesn't really, because if A-star search can improve some problem, well, A-star search improves the problem by prioritizing the things in the frontier that are getting close to the goal. That really doesn't have anything to do with whether or not there's uniform cost in the actions. So A-star search is intended to improve over breadth-first search or uniform cost search. The answer is yes. If some actions incur negative cost, does uniform cost search still guarantee to find the optimal solution? This one was almost more of a were you paying attention during the lecture type question. And I hate those. I'd rather do you understand the algorithm ones. But here's the case where it doesn't. A negative cost implies that you can reduce your total cost so far by taking another step, right? Well, what if there's a negative cost just past the goal? Then the best thing to do is take a step past the goal, pick up your bonus points, and then go back and pick up and go to the goal. Well, since uniform cost search stops the moment it finds the goal and doesn't walk around past the goal before it finds the goal, it would never see that. Therefore, the answer is no. Kind of asked it twice, sort of. Okay, is the purpose to make it robust to negative costs? Nope. Is it to improve the quality of the solution? No, it doesn't improve the quality. It improves the speed by which you find it. Does it reduce both computational cost and memory requirements? Yup. Does it promote diversity? What? Does it compute the Manhattan distance to the goal? Again, that's an implementation detail. That is a good way to implement a heuristic. That's not the same thing as being the purpose of the heuristic. In fact, so this is a way to get there. This is we're asking where we're trying to get. Is it to compute Euclidean distance to the goal? Yet another way to get there. Is it to reparent states when a lower cost path to them is found? So this is a reference to something that is necessary to do to make uniform cost search technically optimal when modifying breadth-first search. It's kind of in there, but it's certainly not the purpose of A-star search. So that's the answer we're looking for. Alice wants to make uniform cost search more efficient, but cannot find a useful heuristic. Poor Alice. She plans to simultaneously search from the start to the goal and from the goal to the start, then merge the two paths when the two frontiers meet. So let's do a diagram. For each of the following pairs of statements, circle the one that is more correct in characterizing the proposed algorithm. So here's the start point, here's the goal point, boom, and we're going to kind of search with two frontiers. We'll assume for now it's breadth first, so they're kind of spherical. Right about there. That's about centered. Perfect. Good enough. And so we'll have these paths that reach from there to there, and these paths that reach from there to there. Right at the moment the frontiers meet, have we found a path from the start to the goal? Okay. If all actions were reversible, then this could be made to work. Or, nope, it couldn't be made to work. Could it or couldn't it? Yeah, it's the first one. Because, but yeah, it does require that the actions be reversible because, yeah, there are examples, there are certainly actions where there are not reversible actions. So suppose instead of taking steps, because in the physical world, you can always back up a step, right? But that's not always true with, say, break a stick in half. Now, unbreak the stick. Whoa, how do you do that, right? Yeah, state something, then recall your words. There's lots of things in the real world you can't undo. And in AI, I hope I can convey to you, we're not always searching walking paths. The AI is not about walking paths, and yet we always do walking paths. Why do we do walking paths? Because students can get it in their head and they understand it. But yeah, that's true, we didn't. And I did that on purpose because I wanted to make it clear that you can search for things that are not paths. And I hope that really is solid in your head, because usually when people are doing AI, it's because they want to do something interesting like, I don't know, you're trying to create documents or compose things or wash dishes or control robots or drive cars. It's almost never walking paths unless you're in the video game industry. That's where we pretty much need walking paths a lot. Or if you work for iRobot and you're making vacuum cleaners, they probably do it for that. Okay. This approach would find a path, but it would not be the optimal. This approach would find the optimal path. Would this be the optimal path? I think it would. The one thing people would get worked up about is, what about the possibility of off by one issues right at the conjunction or something like that, right? Isn't that the only possibility? Yeah, as long as you took care of that carefully, I don't see why that wouldn't be the case. And yeah, you do have those issues just finding the normal path. And yeah, you'd have to be careful, but this would be the optimal path. And if anyone says otherwise, I'd love to hear your argument. This approach would incur a lower cost, computational cost than uniform cost search. This would incur a higher cost. By the time uniform cost search got there, the frontier would have to be basically surrounding the starting point and reaching the ending point. This is a known technique for reducing the computational cost of uniform cost search, and it does reduce the cost usually.